Um, for face-to-face students, for you guys, except if you're online and looking at this, the midterm is going to be Wednesday, September 27th, which is 2 weeks from today. Right? So we're going to cover recursion, and then we are going to do reviews, and we are going to. The 27th, yes, 2 weeks from today. If you're online, I'll be sending you an email. If you can come on that day, that would be amazing. If you are not in the metro area or you cannot come, then we'll figure something out. And I'll be sending details to the online people. If you can come on that date, then that is amazing. Because it makes my life so much easier. Oh, a reminder, let me make the announcement for everybody, that includes you guys. I'm an equal opportunity lawyer, so I require you to show me an ID, a photo ID, when you give me your exam. I have no clue who you are, right? You could be somebody else using a different name or something. So I just ask you to show me your ID. It doesn't have to be your KSU ID, driver's license, passport, something like that.
Okay, it says so on the exam.
Sorry?
It says so on the exam, so I won't forget.
It probably doesn't say so on the exam, but I will not let you forget. It's just some people actually don't carry their IDs.
Young people.
Young people. No, actually, people who live on campus may just, right, walk through here without their ID. Basically people who didn't come in a car, right? Because if you drove a car here, then you probably have your driver's license on your pocket or on your purse or something like that. But if you didn't, then you may or may not have it, right? So, bring it. Okay. Let me talk about recursion, which is the coolest thing ever. We have seen that you can call functions, right? You can call a function, you pass it some parameters, and that function does stuff, right? And eventually it gives you a value back, returns a value, right? Well, that function can call other functions, right? We have seen it, no big deal. Max3 calls max2, right? It's easy to do that way, right? So good? Well, the other function that it can call is itself. And then your brain breaks. That's supposed to happen. We use recursion all the time in real life, right? Both in computers and in real life. How do you define your boss? Well, who's your boss? Well, you know who your boss is, right? Hopefully. If you work, you know who your boss is. Or actually, how do you define your parents? You know who your parents are, probably. How do you define your ancestors? Parents of parents of parents. How do you eventually stop? Well, you say, okay, it's either my parents or their ancestors, right? And so you never have to stop. Does that make sense? I have no clue who they are beyond 2 or 3 generations, right? But they exist, right? Up to who knows when. Up to Adam and Eve. Base case. There's a base case. Adam and Eve. Yes. How does it work with supervisions, with bosses, right? Well, who is my boss? Well, either my direct boss or their boss, right? Until you get to God, to the CEO or whatever they call the top, the root of the hierarchy, right? Does that idea make sense? So we use recursion all the time in real life. We don't see it. That's terrible, right? It's not that common. So what's going to happen, right? How does Java deal with it, right? Java doesn't care. It just calls the function and calculates the value and returns the value and plugs it in, right? How does your function has to be structured um, so it doesn't terribly suck, right? Um, if sorry, you need to know when to stop, right? How do we know when to stop? What's that in programming? But what's it gonna look on if something, right? If you should stop, right? Then return a well-known value, right? That's your base case. That's something that's so simple you know how to solve it immediately. You don't need to calculate it, right? And then if it's not that base case, then you use the same function to calculate the value, right? You normally want to change the parameters. If you don't change the parameters, right, when you're calling the function, then you're going to get the exact same result. That's going to be bad. You change the parameters, usually to a smaller problem, right? And then you do something with that solution to produce the solution to the actual problem that you wanted. Does that idea make some sense? The standard example in math is factorial, right? Depending on how you did math, right? They either define the factorial function as 1 times 2 times 3 dot 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 times n, or n factorial equals n times n minus 1 factorial, right? With the thing that 0 factorial is 1. Which way did you see it in math? You don't remember math.
The other way.
The first one or the second one? Did you see the recursive definition or the other one?
If it's like high school, they show you the first one.
Okay. Cool. It's the same thing, right? And the second definition, this one, is almost programming, right? It's telling me I have an if statement, right? I have my base case, 0 factorial is 1, right? And then I have my recursion. So in programming, this would look like this. I'm defining a function. It's called factorial. It takes a parameter n, right, that I'm calling inside the function n. So inside the function I check, and I am paranoid about things being outside of my if statement, so I ending up in infinite recursion territory. So I'm doing n less than or equal to 0, right? What's the factorial of a negative number? I don't know, you can go learn math, but for now we are going to define it as 0, right? So that's just going to be, if you pass me a negative number, I'm going to do dumb things, but I'm not going to die, right? If it's 0 or less, I'm going to return 1. If the base case, right, the factorial of 0 is 1, I'm done. Now, what if it's not? What if it's bigger than 1? Well, I'm going to calculate it, right? I'm going to return n times the factorial of n minus 1, which is basically this definition, right? Except that I need to write it in programming, so I need to write factorial of n minus 1 instead of n minus 1 back. Isn't this cool? It works by magic. So imagine that I'm asking it, calculate the factorial of 4. This is going to do is say, factorial of 4 is n0. No, so it's 4. Then return 4 times the factorial of 3. Oh, so let's go calculate factorial of 3. Factorial of 3 is n0, right? And the way this works, if you're taking the computer architecture class, right, you have a stack. The way it works is by putting things onto a stack, right? So the stack keeps growing and eventually unwinds the stack until it returns the right value. It puts this factorial of 0. Okay, let me open a stack frame. I go calculate factorial of 3, and when I'm done, I return it and plug it into this. So the stack is kind of where it keeps track of where is it going. Is then 0? No, it is 3, so I'm going to return 3 times the factorial of 2. So open a stack frame, go calculate factorial of 2, and 0, no, it's 2. Return 2 times factorial of 1. Factorial of 1 is then 0. No, it is 1. So return 1 times factorial of 0. Then 0, yes, so return 1. So now this guy, right? Factorial of 0 return 1, so this is going to return 1 times 1 in here. So it's going to be 2 times 1. So in here, factorial of 2 is 2. So I'm going to return 6, and here I'm going to return 4 times 6, which is 24. Does this make sense? Is this cool or what? And even cooler things, with recursion, you can compute everything. You don't need loops, you don't need anything but recursion. An if statement, right? Doesn't mean that you should, but you can. In fact, in this week, you're going to be doing it. And since we haven't seen very complicated stuff, you're going to be doing it on stuff that really should be done with loops. But some things are actually a lot easier to understand with recursion. And when you get recursion, it makes your life so much easier. If you have never seen loops, life is good. Learn recursion first. If you have seen loops, believe me, learning recursion will make you a better programmer. Learn recursion, don't just complain about it and do it with loops, right? Although most of the stuff that we're going to be doing right now could be done with loops. As another example, we can calculate, let me actually go do this stuff. Do new class. These are the magical incantations for defining a main. So I'm going to cut and paste factorial first. And I need to make this static because main is static. We'll see what this actually means later. Let me add to this thing so this would print factorial n equals 5, then factorial n equals 4, then factorial n equals 3, right? And eventually would print factorial 5, which is this makes some sense. Sorry? At the end, it printed 120. Yeah, 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 yeah. You can't tell me. That's why they do that. Does this make sense? Now let's do another example. Let's calculate let's raise some number to some exponent, right? So I'm going to raise 3 to the second power, 3 to the fourth power, those kinds of things, right? How can we do this recursively? What's our base case? What do we know? 3 to the what do we know? Sorry? 3 to the 0 would give me what? 1, right? Is that what you were saying? Cool. So, how do I put this in programming? If what is 0? Is it base or exponent? What do I return? Right? Else, what do I return? Okay. How can I express 3 to the 5th power, right, in terms of 3 to the 4th power?
3 times 3 to the power of 4.
Right? Does that make sense? 3 to the 5th is just 3 times 3 to the 4th, right? 3 to the 4th is going to be 3 times 3 to the 3 and so on. Does that idea make sense? In these more general terms, a base to the exponent is going to be what? Base times a base raised to the power of exponent minus 1, right? Wouldn't it be cool if I had a function that calculates a base raised to an exponent? Oh, I do. What's the name of that function? Power, right? So do power of base to exponent minus 1. Does this make sense? It only works for positive numbers. I die if you pass me a negative. I can do several things. I tend to do this because I'm scared. It's still right. It's only required to work for positive numbers. Definitely would not work for negative exponents because that's right 1 to the something. That's fractions.
Well, you have to return a non-int first of all.
Yeah. But this makes it suck but not die. Whereas if I have it like this, if you pass it a negative exponent, right, yeah, it's gonna go into an infinite recursion. Whereas this would give you 1. Which is wrong, but not terribly wrong. Right? Yeah. We could do other things. Let's see. And let's start playing. Double power. I could do this, right? Yeah. My exponent still has to be an int, right? So what I could do in here is have one more case. Exponent is less than 0, I return 1 divided by power So now I have something more complicated, right, with more cases, and it's perfectly okay.
I think it works even if you turn an exponent into a double, right?
And not really,
Oh, that takes harder.
because you wouldn't reach 0.
Oh yeah, you're right.
Right? So there is some definition for exponents that are fractional, right? I just don't know what it is. It's a summation or something like that. You need to know math, not programming. It's math, not programming. Yes. Does this idea make sense? Wouldn't make sense without doubles because I would just return 0 regardless. But see if this actually works. We can do some easy stuff. 2 to the power of 10. It's going to return what? Oh, I need to make it static. It's complaining that it's not static. Yep. The other way around.
And the other class, he keeps asking us, let's do the 30th, let's do the 20th.
Yes. Right? You should, if you haven't done so, right, you should almost memorize powers of 2 till at least 10 or 15, right? And you should memorize, because this one is really important, 2 to the 10 is what? 1024. Why is this important?
Because it's like a kilobyte.
Because it allows you to map from powers of 2 to powers of 10 within, right, a few percentage points, right? 2 to the 20 is going to be what? A million-ish, right? 2 to the 30 is going to be what? A billion-ish, right? So every 10 is 3 zeros, right? Every 10 twos is 3 zeros. So that allows you to convert easily. Which is useful for kind of getting the idea, right? You can get the numbers. But isn't recursion cool? So this is power, right? In recursive functions that work, right, we need one or more base cases, right? We know the result. We can calculate it without a recursive call. Most of the time we know it. For the simple stuff, right, we know it, and that's it. There is also one or more recursive calls, right? So we'll have an if statement. If it's a base case, if it's something that we know, we just return a value. If not, we will calculate, right? We'll call the same function, right, with different arguments, and usually smaller for some values of smaller, right? Maybe bigger, right? But it's closer to the solution, closer to the base case, right? We just need to make sure that we actually hit the base case. Actually, let me change this to something that's actually more useful. Let's do print countdown, and I'm gonna pass it a print stream. Let's rebuild it. I'm gonna print the count until we get to 0 and not print 0. Which is may or may not be the example. Similar to the example in the notes, right? So what do? What's our base case?
We're counting down.
We're counting down till we reach 0, right? So what's my base case? is going to be 0, right? So
Print
if
0, or do you want to?
from is 0, I don't want to print anything. So what do I do? Just return. It's void. I'm not returning a value. So return just says get out of the function, right? I could actually just write the else clause, right? Let's write it this way, and then we'll come write it a different way. Else, what do I do? Here we are really not producing a value. We are doing void, right? So we are doing stuff to out. So what do I need to do to out? Imagine that from is 3. What do you need to do?
Call the function for 3 minus 1.
Well, but then you also need to do what? What do you do to from? You need to print from. Print this guy, so print 3, and then call the function, right? Print countdown, pass it the print stream, and pass him from -1. Does that make sense? No? Okay, imagine that you pass it with 3, right? What's it gonna say? Is it 0? No. Come here, print the number 3, then call print countdown with the number 2. So is it 0? No, it's 2. Print the number 2 and call it with 1. Is it 0? No, it's 1. Print the number 2 and call it with 0. Oh, it is 0, so I'm done. And then it unwinds the stack.
It's almost like you're like winding this thing up, and you create all this attention, and then like does it all.
Yeah.
It's a little hard to like keep track in your mind. It's like loops seem easier to me. Right?
Yes, because you have done 5 million loops.
Yeah.
Right? Yes. It's actually right. I mean,
you say that it's good to like just do a bunch of stuff like to avoid loops and just do a bunch of recursions now, and later on when you're doing more complicated stuff, it'll be more natural.
when for certain things you need recursion, right? In here we are doing it just to put it before loops, just to not destroy your mind with loops.
Yeah, my mind's already destroyed with loops. So.
Yes, you are actually going to have a harder time with recursion. You're at a disadvantage because you're going to try to keep doing it with loops. So don't just forget that loops exist and do it with recursion.
But every problem, does it have a possibility to be done by recursive?
Yes, recursion is actually, because we are cheating, right? Recursion is more powerful than loops. Because recursion has this idea of infinite memory, right? My stack is infinite. So if I had an infinite stack that never fills up, recursion is more powerful than loops.
But to bring the pattern, special problem of the real world, it is possible to convert recursively.
Can you always convert recursion to loops? Is that what you're asking?
Can
Every loop thing be done with recursion? Yes. There is, and you guys will probably see at some point in time, actually you probably won't see it. I'm lying to you, but let me, if you're doing CS, definitely, possibly if you're doing software engineering, you have a class called Theory of Computation, right? It is somewhat similar to discrete math. It's the adult version of discrete math that you may be taking. In that class, you will see Turing machines, which are a generalization of the concept of computer. It's kind of the simplest possible computer, but at the same time it has infinite memory. And Turing machines are kind of our definition of computation. They are as powerful as any computer, but they are more powerful because they're math. And so they have an infinite amount of memory, whereas your computer has a finite amount of memory. It's not quite infinite. It could be huge, but it still eventually ends, right? So Turing machines are the most powerful computational devices we have. recursive functions are equivalent to Turing machines. And in the 60s, mathematicians proved that these two things are equivalent power. Everything that can be computed with recursive function can be computed with a Turing machine and vice versa. So if you have infinite memory, right, then you can do all sorts of things either way. So recursion is as powerful as loops. If you cheat and you say recursion has infinite memory but loops don't, then recursion is more powerful than loops. If you don't cheat and say, right, you could always build a stack and do it with loops, but it's a pain in the neck. For problems that are easy to do recursively, trying to do them with loops is horrible. In fact, it doesn't work. Like, it becomes super complicated, right? Not factorial or this. In fact, we're going to do one or two that are slightly more interesting. So let's call print countdown, right? How do I call it? I don't do anything with this result because it returns voice, right? So I have to pass it a print stream like system.out, and then let's pass it 5.
Essentially, you do the opposite. You do from +1 and then change the from 0 to like whatever number you want to count to.
If we want to count up,
Yeah.
yes. We can also cheat. What happens if we do this?
So it won't print the first one.
What would print first? We would call print countdown.
It would only. Print in reverse order, maybe?
Yes. It would print, and printing down, this would actually count up. Isn't this cool?
Yeah,
Isn't-
but it's hard to think about, you know? It takes a
It's not hard to think about. It's super easy to think about, right? Just call print countdown and then print the number. It's
Now,
super easy, right? I mean, just
I'm just gonna write it in a ton of loops.
so the first time it didn't take off 1.
so we pass it with 5, right?
Pass in 5, it says, okay, print count output.
Print
from-
countdown from
okay,
4.
You got from a 5, you got a 5, you already subtract 1, but it print 5. How it print 5 right there? It's supposed to be 4.
It didn't print. What do you mean? You can pass it with 5, right?
Yeah.
It's gonna call print countdown with 4.
Oh, it's gonna complete the loop. Then
There is no
start-
loop. It's recursion.
It's finish the recursion and save it somewhere. So
It's saving it in a stack, right?
Okay.
It's saving in a stack. Where is it, and where does it have to come
So,
back, right?
That time is not printing. It just keep doing.
Keeps going, right, until I get to 0.
It,
Then
it
it
keep
returns,
doing it.
and then I was supposed to print 1. Now let me print 1 and
So-
return. Oh, I was supposed to print 2. Now I print 2.
Okay. Now I got it right there.
Cool. Isn't this cool? Yes, it is. You know it is. Let me-
So where is save it? Where somewhere in the stack in the memory. Stack it.
Yes, you will see in computer architecture, right? What's a stack? Imagine a stack of plates, right? Just put one right on top, then you can take out only the one at the top, right? Have you seen, usually like Chinese buffets have actually stacks of plates, right? Have you seen, and they actually go down? When they put a big stack, they go down. So you always have it kind of at the top. Have you seen those things with plates? Yeah. It's the same idea. So the computer has a stack which is just an array of memory, right? It's just memory, and what it stores is the local variables, right? And then when it calls another function, it stores the address of the instruction that it should execute next. Then calling the other function puts the local variables and parameters for the other function into the stack, right? And so when it gets out of the function, it just decreases the stack pointer by however many bytes it needed for all those variables. And that's where, and now go back to this address.
But this is like first in, last out.
Yes, but it depends, right? It just calls the function.
Yeah,
You don't
yeah.
terribly care, right? In terms of math, it just calls the function, right? I mean, you don't terribly care. For purposes of this class, you can think of it as it's just magic and I don't need to know what it does, right? I like to join it with computer architecture, right? And we're actually going to talk about a slightly different concept, but so now let me put it back to where it was, so we count down rather than up, right? And we could actually write it like this, because that's actually slightly dumb. If from greater than 0, so this is prettier.
The assumption that we would get any negative numbers,
Sorry?
with the assumption that we wouldn't try to
You can call it with negative numbers. What does it do? Count down from -5 until you reach 1. What should you do? What? You just don't count, right? That's it. I'm already there. And this would do the right thing, right? So happens if I pass -5. Nothing happens. So it actually works for negative numbers. But it's a good idea to always ask yourself, what are my assumptions? Does it work with negatives? Does it work with 0, right? What am I passing? That's a very good thing to do. Is this cool or what? Now let's make it how do we do it so that we count down from to 2, right? What would change? Rather than counting to 0, right? I'm counting to 2. To this, my second parameter. Actually, does from and to confuse you? Should we call them like low and high? To me, from and to makes sense, but good enough, or does it confuse you? From and to is good enough. So what do I need to change? And then here, what do I do? Passing from -1, and what do I do with that 2? Do I change it? Or do I pass it the same? Right now,
If we want to go the opposite direction, we're going to change from minus to plus, or from.
we are still counting down.
Oh, okay. This is the same thing. It's to 2.
How about you do increments and by plus 2?
Well, actually,
Or
you could
repeat
increment, but should I increment? Or do I still want to count to the same number? Should my limit change? See what happens when I print from 10 to 5. It will not print 5. Maybe I wanted to print 5.
Well, then I guess you got to do 2 minus 1 if you wanted to print the 2.
Yeah. Or how can I change it so that it print 2? What would change?
Greater than 2.
Yep. So what if we want to count up in a reasonable way? What does it change? Now from is going to be less than 2, right? So is my condition the same? It's inverted, right? Of course, called print count up instead of print count down. And then what do I do here? What happens if I do this same thing? Is this correct? What's going to happen? I'm start with 10, right? And then oh, it should start with like 5. I want to count from 5 to 10, right? What's going to happen? Something's going to happen. It's from less than or equal to 2. Yes, yes it is, right? So print it and now call it with 4, right? Then when it goes again, it's gonna keep going forever. Let's destroy my machine. I get an exception that says, your stack is too big. After something like maybe 10,000 things, I get a stack overflow error. Close to 10,000 things, right? So yes, my RAM is not infinite, but I can call 10,000, right? A nest of 10,000-ish functions.
Does Java detect when there must be something that's infinite, an infinite loop or something, or does it just wait until it runs out of memory?
Yes, it waits until it runs out of memory. There is no way, actually, in that theory of com class, you will see that there is no way to prove anything about anything. There is no interesting property of programs that can be proved. You cannot prove that for general programs in C or Java or something like that, you cannot prove that they don't have infinite loops or anything like that. It is impossible to prove that stuff. You can restrict your programs and say, okay, I'll make this language so you cannot write infinite loops, but you can also not write very interesting things. So it basically just waits. If you have a loop and it never actually ends, then you would just keep going forever until you press Control C or go to the task manager and kill the thing or something like that. Because again, it doesn't know whether you wanted to run that thing for hours, right? Maybe you do. It's a game and you're playing and you play for hours. How does it know whether you wanted to or not? Does recursion make sense? Some sense, right? you can do these kinds of things that you could do with loops, right? And you can count up or down, or do other things here, like maybe print twice this thing, right? Or something like that, right? Oh, I need to do, what do I need to change so that this thing works, actually? We never changed it so it works. This, right? Is it okay to call from plus plus instead of from plus one? To do from plus plus instead of from plus one?
Yes.
It is okay-ish, but it's considered bad manners. It's considered bad style, right? Why the heck are you changing it, right? You're passing it to the next guy. You don't need to change it here. Just pass it to the next guy. Don't have side effects. Just in case you're going to use it later, right? It's kind of, it's possible, but bad manners. Make sense? Now let's see. Let me make sure that, yeah, more counting and printing. Oh, accumulators are cool. Yeah. There is, let's go play with power. All the way, right? Power is simple to understand. I'm gonna eliminate this negative thingy. I'm gonna change its name. Now it still works, right? I just eliminated negative to make it simpler. A slightly it's not inefficient, but it's not optimizable thing, right? In here, I still need to do, once you return this, this value, I still need to do things to it. So I really need to keep this stack, right? If I didn't do anything with it and I just returned the value that this function returns, then I don't really need to keep this stack, and I don't need to create a new stack frame. I can reuse the same stack frame if the compiler was smart enough. Does that make sense? So one thing that I can do is have a current value here, and what I'm gonna do here is I can only here I want to be able to just say power accum of something, right? So one thing that I can do is base times current value, and then in here I'm gonna return current value. I need to figure out the other thing, but oh well. See if I still remember my C++. Um, what's hopefully going to happen? Let me just flash it. Did it print stuff? Yeah, it printed stuff. I still sort of kind of remember that stuff. Let me add spacing to make it prettier. So it says you call power accum with 2 to the power of 3 and you have 1, right? And here I'm counting down. That's my exponent. But the current value is being multiplied by the base, right? So I'm calculating that power. In the end, current value is going to have the actual power. Does that make sense? What is the cost of doing this? I have a mental cost. This is actually more complicated than the other power function, right? What is the possible advantage? Java may be able to optimize this into something that's much more efficient. Is it worth it? I don't know, it depends. But it's one more tool in your arsenal. This, in most of the literature, this is called an accumulator, right? Does this idea make sense? Did I copy power? No. Now, let's do something that would actually be a pain without. Oh, actually, let me mention one more thing. In here, the caller needs to pass me this thing, right? The initial accumulator value, that's not very useful. They don't really need it. They don't care. They need to know that they always pass me a 1.
Yeah.
So a common thing is to write a wrapper function.
It just alerts them to what they're supposed to do.
No, that just provides the right thing, the right interface.
Oh,
And-
so they don't even have to know, it'll just automatically do it.
Right? And they don't even need to know that this one exists.
Oh, that's so elegant when you put the, when you have the different, the 2 parameter and the 3 parameter one.
It is sometimes confusing to overload your functions, but it's sometimes just elegant and pretty, right?
Yeah, I don't know why I didn't think of that myself.
But and normally when you later on we'll see that you can have private methods and things like that that nobody else is able to call, so you would make that one private so that they cannot even call it. They cannot call it wrong. But that's for later. Now, there is a cooler, and I think I have it here. Please tell me I have it. Yeah! A cooler way of recursion, actually, this one would be a pain in the neck to do without recursion. So this one is a good use of recursion. When we're raising a power, right, of a base to some exponent, I'm still going to have the same thing, right? it's going to be 1 if n is 0, but now I can go and look at the exponent and say, okay, if you're raising something to the 10th power, right? What can I do? Well, I can raise it to the 5th power and then square it, right? And that's going to raise it to the 10th power. Does that make sense? So now I have two cases. If we're raising something to the 10th power, then I can raise it to the 5th and square it. If we're raising something to the 11th power, what do I have to do? I can't raise it to the 5.5 power, right? But what can I do? Raise it to the 5th power, square it, and multiply it once more by the base. Does that make sense? So I'm going to have, is it even or is it odd, right? And depending on that, I'm going to do different stuff. So, power, let me call it half. How do I know if a number is even? Let's do power half of what? The base to which exponent now? Right? And so if is even exponent, what do I return?
Power half.
So if it's not even, then it's odd, what do I return?
The base times half power.
Good.
But why is it good to do it this way?
Well, this is more complicated, right? Let's see. Oops. I just deleted the other guy. Do I suck that much? Yes, I do. So I'm going to have to delete this guy too. Let's raise something to the 30th power, right? That should give me somewhere, it's 1.01, right? So it's a little bit more than 1.3, 1.30, right? Because if I use bigger numbers than I get, right? How long does it take me to raise this, right? To calculate this stuff with this guy?
Pretty fast because the computer's doing it.
Well, computer is fast, but about how many operations do I need to do? How many times do I call power?
30 times.
30 times, right? Okay. So we tend to call that linear time, order of n, right? You will see in data structures and algorithms, order of, right? So it's about n. If your exponent is n, it's about n times, right? If you have a bigger, if you're doing 300 instead of 30, then it's going to take 300 operations, right? Which is still nothing because computers are super fast, but now compound interest would work. Right now I got 19, but what if I do power half instead of power, right? how many times do I call it?
I guess 2 times.
I call it with
so then
300, right? And then what's going to do? 150, then 75, then 37, then 18, then 9, then 4, then 2, then 1. 9 times instead of 300. Isn't that cool? Every time I'm halving my exponent, right? So that is logarithmic, right? The time is proportional to the logarithm base 2 of n. So if I have 1024, right? What's that gonna do? It's only gonna take me 10 operations, right? Instead of 1,000. At some point in time, I'm gonna break, but it's not breaking that much. So if I call power half, I'm only doing 10 things. If I call power, I'm doing 1,024 operations. This one is much faster, right? Does it matter? No, right? In this particular case, no. It's from super fast to super fast, right? But if I'm calculating this a ton of times, then it may matter, right? If I'm doing it for different operations or something like that, then it may matter. Does that make sense? Is this cool or what? This is actually a useful application of recursion. Try to do this with a loop and not get utterly confused. It's doable. It's just horrible. I don't even know how. I don't even think that I could easily do it with a loop. You can, it's just a pain. You need to keep a stack. This is why you need recursion. So this is a much more useful example of recursion, right? We need to do the simple ones first. Some other things, and I'm gonna cheat, right? Most of the stuff that have to do with loops and recursion and things like that, you need something to compute on, right? Computing on numbers is okay, and that's kind of what we have been doing, but you normally want to do bunches of stuff. I don't want to cheat and start with arrays, right? I don't want to do arrays yet. We'll talk about arrays and what they are. But we can slightly cheat and do stuff with strings, right? What's a string? Well, it's a bunch of letters, right? It's a bunch of characters. It can tell me its length, and it can tell me char at, right, would return the character at a given index. And so I can write contains, does a string S contains a character C? I need something to recurse on, right? And so I'm gonna say, does it contain the character C from this index, right? So want to do from this index, let's do from this index till the end of the string. Does that make sense? how can we know that it doesn't? Well, what are our base cases, right? Well, how do we know that it does contain it? What's the easiest, right, way that we could know that it contains it?
If the first character is equal,
If the character, right, at from is that one. How do we know that it doesn't contain it?
you look through all the characters and
So what's gonna be from? From is gonna be
uh,
the length of the string. If it's greater than the length, right? If the string contains 5 characters, it doesn't contain whichever character you want from character 6 on, because there is no character 6. Does that make sense? So if it's greater than or equal to length, what do I return? False, right?
but from doesn't equal the length. From's gonna start at 0.
But eventually, right,
Eventually will equal length. Yeah.
it will equal the length. That's my way of, right? That's one way of ending. Then I need to do, let's do it like this, and maybe we'll see if car at, oh, let's do car at. If it's equal to C, right, then what do I know? It does contain it, so what can I return?
C, so you return true.
If it's not there, then what can I return? I know that it's not at from, but it could be starting at which character?
You return the next character.
It could be starting at from plus 1, right? So I need to check whether the string starting at from plus 1 contains the character, right? Wouldn't it be cool if I had a function that would tell me that? Do I have that function? String contains, right? Does this make sense? May even work. But does it make sense? And then we'll sort of kind of makes sense. Let's see if it actually works. Sorry?
There's too many brackets.
Well, I would normally do this. Or I would take out the brackets, but we're not supposed to do that. The other thing that you could do is think of it as chained rather than nested, or else ifs, yeah.
Yeah, there are too many brackets.
Well, that depends. It was nested.
Okay.
Now it's chained.
It's hard for me to count them all up.
Also, since we are returning, this is not really necessary. That would be another way of writing it. So we should print true, false. Or die. Yeah, true and false.
Oh, okay, wait. Okay. Well, that's the problem. Return 2 things.
No, I printed 2 things.
Oh, you printed.
Does this make sense?
Why the second one print false?
Okay, I call it with this string A and C, right? The character D and 0 comes and checks. Is 0 greater than the length? What's the length? 3. So it's not, right? Okay. Is s.char at of 0 equals to D? No, it is A, right? So I'll return string contains the same string, the same character, but now the number 1, right? Is 1 greater than the length, greater than or equal than the length, which is 3? No. Is s.char at 1, which is what? N, is it equal to D? No. Then return string contains of s, c, and 2. Is it greater than or equal to length? No, right? Is s.char at of 2, which is c, equal to the parameter c, not the letter c, right? So, which is the letter D? Is it equal? No, right? Then I return string contains of the string, the C, and now 4. Right? Sorry, 3.
3.
Is greater than or equal to length? Yes, it is. So I return false.
So that last log return string contains, that's basically like, that's like kind of like searching through.
That's the recursion. That's the recursive part, yeah. That's searching through the rest of the string. Isn't this cool? Yeah, good. And we would normally write a wrapper, right? So that they don't need to know where they pass 0 or something like that. As an exercise, do it the other way around. Start from the high, right, and go all the way down to 0. Right? Play with this stuff. That's what's gonna make it make sense, right? In summary, a recursive function calls itself, right? We normally define a recursive function with one or more base cases where we know the answer, and one or more recursive calls where we call the same function but with different values for the parameters. If our recursive function needs extra arguments, we normally write a wrapper function that calls the recursive one with the extra arguments, so the poor user doesn't need to know what the heck we did. Does that make sense? Cool. Assignment 4 awaits you. Not that bad, right? Assignment 4 is about recursion. So I will see you guys on Monday.